All right. Okay, my name is Peter Frøystad, and I work as a blockchain researcher for EVRY here in Norway, an IT company that delivers IT solutions to a lot of Norwegians, Norway's biggest bank, and also, of course, in the Nordics. Since this is a lightning talk, I decided to let a lot of the other presenters here give you an introduction to the different use cases and applications of blockchain technology. And I wanted to give you guys here in the audience a bit of a technical primer and looking a bit into the blockchains from a technical side. Well, how are they different from what we know as databases, centralized databases, and what is new about them, and what can they do and what can they actually not do. So just start out by defining what I mean by a database, of course. Hopefully a lot of people here know what it is. It's a repository of structured information organized into tables. And the most important aspects of a database are the rules about the data stored within. And these rules take a number of different forms, such as this database scheme, which defines the kind of information that is permitted in each column. There's unique keys, check constraints, which enforce relationship between column values in each row, and of course foreign keys, which enforce relationship between tables. And all of this is changed by transactions, which is a collection of changes to a database that is accepted or rejected as a whole. And every time a transaction modifies the database, the software ensures that the database rules are ensured. If any part of the transaction violates one of these rules, the entire transaction will be rejected. Basically boiling down to what these rules do is answering the question, is the database in a valid state at this point in time? And this works just fine if a database sits inside a single organization because the main job of the constraints is to prevent program error. What it doesn't do is fixing the problem of trust when you want to share a database across boundaries. Because let's see what happens if we want to, if two or more parties want to share a database which none of the parties controls. It can be written to by any party, and you can be relied upon by everyone. And to make things worse, let's make sure the parties have different incentives, they don't necessarily trust each other, and they may even be fierce competitors. And in this case, the solution has pretty much always been the same. You introduce a trusted intermediary, and this intermediary manages a database centrally, provides accounts to all the parties, and ensures that the operations are permitted according to a known set of rules. And in many cases, especially financial, every party still maintains their own copy of the database and spends a lot of time checking these against each other, making sure that their databases agree. And that is a lot of what makes the problem. So you kind of had a situation, if you want a shared write database in an environment of limited trust, there's been no good alternatives until now. Because let's say we wanted to allow database to be shared in the right sense without a central authority. What would that look like? And in hint, it looks a lot like a blockchain. Because it starts out with a robust peer-to-peer network that allows transactions to be created by any party and propagated quickly to all other nodes in the network. It needs a way to identify conflicts between transactions, and it will need to resolve them automatically. It will need a method for tagging different pieces of information as belonging to different participants and ensure that all peers, enforcing that this data ownership is made automatically, again, without central authority. And it will need synchronization technology to ensure that all peers converge on an identical copy of the database. You can't have, again, people being out of sync, a database not being the same as each other. And lastly, you also need a paradigm for expressing restrictions on which operations are permitted. For example, you need to be able to prevent one company or one party from inflating the database with fictitious entries such as spam, basically. And that's kind of a tough list right there. And that's simply not supported by many of today's off-the-shelf databases. Current peer-to-peer replication techniques is still kind of clumsy, as a complex approach to conflict resolutions. And standard database level restrictions like unique keys and check constraints cannot protect a database against malicious modifications. So the bottom line is we need a whole bunch of new stuff for shared write databases to work. And it just so happens that blockchains seems to be the best solution for it. Again, I don't really have time to go into too much detail how blockchains do these things, but it's a key element that include regular peer-to-peer techniques, one-way cryptographic hashes, per-row permissions based on public key cryptography, multi-party consensus algorithms, and of course grouping transactions into blocks. What's interesting about this is a long list of tried and tested techniques. None of these techniques by itself is completely new. It's the way it's been combined into a new, wider area of technology that is allowing new innovations from decades-old ideas. So, and in addition to these tried and tested techniques, what is new is a new type of rules that is basically being able to restrict the transformations that a transaction can be performed. And these types of restrictions or rules can be expressed as Bitcoin-style transaction constraints, and of course Ethereum-style smart contracts, which is basically a way of enforcing stored procedures if you're familiar with database technology. And also on IBM they use chain code to the same effect, but it's a lot similar to what they've done in the Ethereum with smart contracts. And each of these have their advantages and disadvantages that you need to look into in the future to try to figure out which is best for each situation you're in. So, bringing it back to what I said at the start, what you've done is you've changed the question from is the database in a valid state into asking, is this a valid transaction? Every transaction is checked against the rules established by every node on the network, and those that fail are rejected and not relayed on. And asset ledgers, a ledger that is being made to keep track of an asset, contains a simple type of example of this type of rule. Basically to prevent a transaction to create an asset out of thin air. The rule states that a total quantity of each asset must be the same before and after every transaction. So yeah, again, you're changing from into the question, is that a valid transaction, more than is it in a valid state? So I wanted to look a bit into the advantages, disadvantages of the new type of database, if you can call that, or blockchains. What do they have an advantage over a traditional classic database? So the core value of a blockchain is enabling a database to be directly shared across boundaries of trust without a central administrator. This is possible because blockchain transactions contain their own proof of validity and their own proof of authorization. And it doesn't need a centralized application logic to enforce those constraints. So transaction can be therefore verified and processed independently by multiple nodes. And the blockchain will act as a consensus mechanism to ensure that those nodes stay in sync. The second benefit of blockchain-powered databases is extreme fault tolerance, which stems from the inbuilt redundancy in a blockchain. Every node processes every transaction, so no node is crucial to the database as a whole. And since also nodes connect to each other in a dense peer-to-peer fashion, many communication links can fail between them before anything's grind to a halt. And also blockchain ensures that nodes which went down for power failure or some other hardware failure can always catch up to the transactions they've missed. But there's something blockchains are maybe not as good at, and it comes to the confidentiality. Because since every node in a blockchain independently verifies and processes every transaction, a node can do this because it has full visibility into the blockchain's current state, and also it has full visibility into what modification is requested by this transaction. So for many applications, especially financial, this full transparency enjoyed by every node can be an absolute deal killer. If a regular database is read control and write control, a blockchain can really only be write controlled. There are, to be fair, a couple of strategies that are available for mitigating these problems. These range from simple ideas like transacting under multiple blockchain addresses to more advanced cryptographic techniques such as confidential transactions and zero-knowledge proofs. But basically these are a bit still in development. But nonetheless, the more information you want to hide on a blockchain, the heavier computational burden you pay to generate and also verify these transactions. And no matter how these techniques develop, there will never be the simple and straightforward method of hiding data completely. And also, blockchains will also always be slower than centralized databases. It's not just that today's database or blockchains are slow because the technology is new and unoptimized, but it's a result of the nature of blockchains themselves. You see, when processing transactions, a blockchain has to do all the same things as a regular database, but it also carries 3 additional burdens, namely in signature verification, in the consensus mechanisms, and of course redundancy that is enjoyed by all the nodes. And but the reason why everybody here in financial world and fintech are talking about how it will make finance faster and cheaper is because they allow to speed up business processes. The technology itself is not faster than what we have, it's just that it enables us to do things we couldn't do before, or allows us to do things faster and cheaper than we could before. So, if you've been able to make sense of me so far, I've kind of tried to frame the blockchain as simply shared databases. Why? Because as a technology, blockchains can be applied to many problems far beyond just tracking financial assets ownership. Any database which has multiple non-trusting writers can be implemented over a blockchain and without requiring a central intermediary. Having said that, at this point in blockchain development, blockchain are mainly the interests of those who track the movement and exchange of financial assets. They are responding basically to the threat maybe that cryptocurrencies face, or like Bitcoin seem to entail, but also because an asset ledger is the most simple and natural example of a shared database with interdependent transactions created by multiple entities. There are, however, a lot of other enterprise use cases that are waiting to be explored. A lot of them are being explored over in the future tech chamber, but they can also be looked at in enterprise settings such as intercompany audit trails, provenance tracking, and supply chain management. I know the guy from IBM talked a bit about that. So if anyone is here and looking for ways to which blockchains can add genuine value to your business, that might be a good place to start. Just make sure that you take a good look at the requirements and the business problem for your project, and you start there to determine whether or not blockchains will be a good fit. It's not every situation that needs a blockchain, but there are a lot of things that can be done more efficiently and better with blockchain in the future. Thank you.